Hi everyone, welcome to Deep Learning Talks. Today we are going to discuss the most important part, the internals and the feed-forward parts of a large language model. We know that large language models can be thought of as nothing but transformers. To be more precise, decoder-only transformers. To be more and more precise, those decoder-only transformers that can generate the next token in an autoregressive fashion, and they are generative in nature, they are predictive in nature, and they take in some inputs and they generate some outputs, right? They have a training phase where they are trained on a global world knowledge data set that is nothing but the whole internet. And then they have an inferencing stage where we inference them, where we query them, during which they simply generate or answer our query, right? So ChatGPT is nothing but an application over such a large language model. Inside ChatGPT, inside the application layer, we have a large language model that is helping us inference and helping us answer all our queries. And how did we make them conversational? So we had a large language model or a neural network or a transformer. I'm using them interchangeably. Let's say this is a function known as f of x. It generates the next token. We put it in a loop in an autoregressive way to keep on generating the new token, so that they act as an autocomplete engine or a sentence continuation engine, right? Now what is happening, we have this autocomplete engine, sentence completion engine. We want to make it conversational. We have another neural network, or basically we train them on a large data set of conversations. What conversations? So some people manually wrote the way humans converse, and they manually wrote human-led conversations. Like for example, let's say, who is the president of XYZ country? What is 2 plus 2? The questions and the answers, the questions and the answers. There were millions of these conversations. And we trained a neural network on millions of these conversations. And we wanted to enforce the conversational behavior on the applications that are, built on top of large language models, right? So, GPT is a foundational model, and then ChatGPT is an application layer on top of that foundational model. So when we interact with ChatGPT, we interact it during the inference phase. So when OpenAI planned to train ChatGPT, that is the training phase. So today we are going to talk about the training phase, especially the feed forward pass. So why do we call it the feed forward pass? So in a neural network, a large language model is nothing but a neural network. A transformer is also a neural network. A convolutional neural network, which can solve images or which can do classification and regression on images, is also a neural network, right? So neural network have multiple forms and shapes, right? And they're able to solve different modalities. That's why we generalize them as neural networks. We also call neural networks as function approximators, right? So a neural network generally has an architecture, and a neural network has a topology and an architecture. For example, a simple neural network, a deep neural network, or an artificial neural network would something be like, an input layer, an hidden layer, and an output layer, right? So this is the topology of a neural network. In case of a transformer, things get a little more complex because we have more and more sublayers, right? So we are going to talk about the feed forward pass, how information flows during training, where does the data come from, what gets done on the data, and how does it go through each subblock, block by block, before it produces a probability, right? And what is the probability? It will produce a probability for the next token from its vocabulary. Let's say the vocabulary is 50 size, 50 tokens. It will assign all of the 50 tokens a probability function. This is a one feed forward pass. One feed forward pass will take in some tokens and generate a probability. We'll talk about the feed forward pass in detail in this video. Now, since we are talking about a specific neural network, which is inside a large language model, we will talk about its particular training now. But we know we have a mental model. We have, let's say, the most complex language model, which is the large language model that we're talking about. It has a forward pass. It has compute loss as step 2 and backpropagate as step 3. When we talk about a simple traditional deep neural network or artificial neural network that has input layer, hidden layer, and let's say output layer, it's training. So any neural network, we should know it will be described using using a topological architecture. What is a topological architecture? It is like a directed acyclic graph. A neural network has some input layer which has input neurons. It has some hidden layers which has some hidden neurons. It has some output layer, some output neurons, right? Output neurons depends on the size of your output classes, right? Let's say if you have 10 classes, you are solving a 10 class classification problem, it's going to have 10 output neurons. And the size of the input depends on the size of input features that you're feeding it at one time. Like let's say each data point is described using 10 features. So the input neurons is going to have 10 neurons, right? Now the hidden is your hyperparameters. It is the choice of the designer, the choice of the scientist, the choice of the engineer. They can, choose whatever they want to. More the hidden layer, more the model complexity. More model complexity also correlates with better performance. Not always. I mean, it's correlation is not causation, but there is a decent amount of correlation when you increase data really well. When you increase the number of hidden layers really well, the neural network possibility and the plausibility of a neural network, to understand the data and to understand the deeper and hierarchical relationship in the data becomes very high, right? So we know every neural network has architecture, so large language model should also have an architecture. Since large language model is a decoder only transformer, which is one level more precise, so neural network is good for people who just want to keep it abstract. But for people who want to go into the depth, this neural network is basically a precise decoder only transformer, right? Whenever we have a decoder only transformer, we do generative stuff. When we have an encoder only transformer, we do representative stuff, which means we take a lot of tokens as input, we generate a lot of tokens as output. In case of encoder only, we take a lot of tokens as input and we generate the token representation, the token embeddings, the expressiveness of the tokens and the meanings of the tokens, right? So that in an encoder only. Right now, we'll fix two large language models. Now, we've set the ground for understanding large language model. Now let's directly come to the feed forward pass, right? So what does a feed forward pass contain? You will take a lot of input, right? So the input is nothing but the text. We talked about the pre-training phase in the previous video. So after doing a lot of pre-training and data collection, you have a lot of data that that will undergo tokenization. Tokenization algorithm like byte pair encoding will convert or will generate a lot of token IDs and tokens, right? Now these token IDs and tokens are not enough. We need token embeddings. Token embeddings will represent the meaning, the meaning of the token in a higher dimension, right? So Puru is a token that can be represented in D dimension. Let's say D is 1024 dimension. That means I will not represent Puru as character P, character U, character R, character U. I will represent Puru as maybe a 512 or a 1024 dimension vector. It's a column vector, right? Now, for every token, I will have token embeddings. Token embeddings along with positional embeddings is going to act as the input. So this is all the feed forward pass, right? This is not backward pass. So we take the embeddings as input, we feed it to the transformer. So the transformer internally is going to multiply or is going to compute attention. It's going to compute one head of attention, two heads of attention, three heads of attention based on all of these tokens, right? To build an opinion on what are the contextual representations among all the tokens, right? Then it is going to do context mixing. So what I mean by context mixing is for all the four output heads, it's going to concatenate them. After it's going to concatenate them, it's going to linearly project them using an output projection matrix, right? So the first step was embeddings. The second step is multi-headed attention. So multi-headed attention will also undergo the context mixing, which is multiplying it by projection matrix. Then we will produce an output, right? Then we will do residual and add normalization. So generally, adding residual and layer normalization happens at every before every sublayer, right? So it's called as it's also called as pre-layer norm, right? So generally both the format works, pre-layer norm and post-layer norm. Pre-layer norm works better in the GPT family, in the generative decoder only family, right? So this operation, which is adding the input to the output of the previous layer, this operation happens. Then layer normalization, which is you normalize and you do some scaling and shifting operations to normalize the scale of all of your input and all the weight matrices that you're dealing with. Now what really happens after this is feed forward pass, which is multi-head attention, residual and layer normalization, then has to give the continuous output to the feed forward neural network. Feed forward neural network will take in the output from the previous block, which was nothing but the multi-headed attention block. Then it is going to again fuse in more non-linearity using its own hidden layers. Generally, let's say we have put in two hidden layers. It's going to do the weighted average of its weights and biases, because the feed forward neural network will have its own weights and biases, right? And then it's going to do the weighted average, which is nothing but, let's say, W transpose X plus B, the simple neural network equation. And along with this, it will also add more and more activation. Then it's going to go to the output head, right? Now the output head is responsible for converting everything to probability mask using softmax function. It is going to, let's say the vocabulary size is 50, it is going to produce 50 probabilities for, let's say we have 50 tokens in the vocabulary. It's going to produce uh, probability for each of the token present in the vocabulary. That will determine what is the token, what is the probability that this token should come. Now we have a choice. We can pick the maximum of all the probabilities, or we can pick randomly. We can sample the max, we can sample randomly the next token, right? Now we have predicted, we're going to compute the loss, right? So feed forward pass is done. Feed forward, when you generate the first output, like this is only one iteration, one phase of one iteration in the training. When you generate the first output, the feed forward pass is done. Now the output probability has been generated for a token. It is time for me to compute the loss. As and when I compute the loss, I can go and update my parameters, right? Because the loss will tell me how bad did I do, right? The loss will give me a score on my performance, right? So this is one set of feed forward pass. In the subsequent video, we can discuss that once the loss is computed, what do we do in the backward pass? Thank you. I hope you liked it.